how to do area between curves using integration. So let's go. Today we're going to learn area between two curves, so we're going to jump right in. The very first thing you have to do when you're given your functions is graph them. So graph them on your calculator and then go ahead and sketch a graph of them on your paper. It is way easier if you're showing your two functions on the paper. So the first thing we're going to do is, how are we going to find the area between two curves? So we're using calculus, and how do we add things up in calculus? Of course, we're going to use integration. So how do you find the area between two curves? We're going to go back to something basic, a rectangle. As you draw in rectangles between these two curves, we all know how to find the area of a rectangle. So that's what we're going to do. In calculus, of course, we add things up using our summation, and we're going to find the area of a rectangle. Base times height. So that's what we're going to do to figure this out. And of course, in calculus, this big integration and all these rectangles, we're actually going to be using tiny, tiny, tiny rectangles stacked right next to each other to find an accurate area between two curves. So the first thing we have to identify here is, what is the base of these rectangles? So let's go over and look. The base is this part right here. These are tiny changes in x values, because of course this is along our x-axis. So these tiny changes in x values, we are going to use our dx, which of course you know you need. So your base is actually your dx of your integral problem. Now, what is the height of these rectangles? Well, the height of these rectangles, the top of these rectangles are hitting this purple function, and the base of these rectangles are hitting our green function. So how do you find the height? Top minus bottom. So your height for these are going to be the top function minus your bottom function. So let's write this out and see what that means. So of course we're going to add up our rectangles, and we know when we multiply, it doesn't matter if we do base or height first, right? And so the base part, that change in x value, is actually going to go at the end, and then our height is the top function minus the bottom function. So what is our top function here? Well, the top function is actually our line. So our top function is x plus 6 minus our bottom function, which happens to be x squared. And so this is our height piece, and now our base piece is dx. The only thing else we have to find are, what are our bounds? All you have to do is look at where these graphs intersect. So what you want to do on your calculator, after you graph them, go to the intersect function, and you can find where these 2 points intersect, or you can do it algebraically, right, and set the equations equal to each other and solve. So you could do this: x squared equals x plus 6. You move these over, x squared minus x minus 6. And you could factor those out to find your two x values and then plug in to find your y values. But since you're using your calculator, just let it do it for you. You'll find that they intersect. This is your -2 value, and your x value here is at 3. And we don't need to know the y values, right? Because this problem is a dx problem. He's your boss. So since it's a dx, your bounds will be in x values. So this will be from -2 to 3. Here is your equation that you need for this problem. The next step is you're going to stick this in your calculator and find the integral. So in your calculator, in y1, you're just going to put x plus 6 minus x squared. You're going to go to your integrate button. You're going to put -2 in for your lower bounds and 3 for your upper bounds to get your answer. And you should get 20.83 repeating. So really, area between curves is super easy. You're finding the area of a rectangle and then integrating on your calculator. Done. Now let's look at this problem. We talked about doing rectangles, but what happens here? If you have a vertical rectangle here, your top minus your bottom is the same function. You would have 0. So we can't do it this way. We're going to have to try another way, which means we're going to have to try rectangles this way to find the area between these two curves. But what does that change for us? Well, now look. We always want to do base times height for these, right? We're going to sum up base times height. The problem is our base is what is changing. Our base is one function minus the other function. And how do you find that difference? You're going to take the one furthest to the right minus the left. So in this problem, our base is actually the function on the right minus the function on the left. And our height is this change right here. Those are tiny changes in y. So this is going to be a dy problem, which means y is your boss and your bounds have to be y bounds. So let's write this function out. So we're going to sum up. Our base is our right function minus our left. So our x minus 2 minus, what do we do over here? And this is a dy, so what does that mean? Yeah, hopefully you're catching on. Because y is the boss, everything here has to be written in terms of y. So I'm going to go back and I'm going to change this. First thing I'm going to do is I'm going to rewrite this equation, and this is going to be y plus 2 equals x. And when we come over here, our function on the right is going to be y plus 2 minus y squared. That's right minus left function. And then we have dy. So now you're looking for your intersection points, and you need your y value intersection points. So your y value down here is -1, and over here, this y value is up here at 2. So you're going to have -1, 2. This would be your answer for your function. Now, what do you put in your calculator? Because you can't put y into your calculator. No worries. In your calculator, you can just replace the y's with x's, and you will still get the same answer. So in your y1 in your calculator, you're just going to put in x plus 2 minus x squared. But make sure you evaluate from -1 to 2. All right? When you do that, you should get 4.5 in your calculator for the area between those two curves. Now I'm going to show you another example. This function, you can either do vertical or horizontal rectangles, because when you do your vertical rectangles, it hits both functions, right? And the same is going to be true with horizontal. So I'm going to show you one function set up two different ways. And just so you know, you can choose. It doesn't matter as long as the rectangles are hitting two different functions. So again, we're going to set up, and this time we're doing vertical. So we're going to do base times height, right? Our base of these, they're tiny x values that are changing. So this is my dx. My height is going to be my top function minus my bottom function. And then I need to find where they intersect. And I'm using my x values because this is a dx problem. Whoever goes with the dx, that's the boss. Okay, and that's who you follow to set up your bounds and which variable you put in your equation. So this x value, of course, is 0 down here. This x value is 2 up there at the top. So we have the integral from 0 to 2. My top function is my g of x is 2x minus my bottom function, x cubed over 2 dx. So this is what you would write on your paper for your equation. Then in your calculator, you'd go ahead and stick in 2x minus x cubed over 2, and you're going to evaluate from 0 to 2, and you should get an answer of 2. So now we're going to look at the same problem, but do horizontal rectangles to show you that it can be done the same way. This time, our rectangles are going to go this way between our two functions, and you will notice then the tiny changes are in our y values, which means this is going to be a dy problem. So y is going to be the boss when you're setting up your bounds and writing out your function. So again, we're going to do base times height. And our base for these equations are going to be the right function minus the left function times our height. And in this case, our height was tiny changes in y, so it's a dy problem. So let's integrate. Our function on the right is our blue function, but notice this function is written in terms of x, and this is a dy problem. So we have to rewrite this in terms of y. So if you have y equals x cubed over 2, multiply 2 on each side. And how do you get rid of a cube? You take the cube root. So you have the cube root of 2y x. And if you're not familiar, you can write 2y to the 1/3 power to make it easier to put in your calculator. So our function on the right is 2y to the 1/3 power minus our function on the left, which again, so this is y equals 2x. Divide both sides by 2, and you get y over 2. And then this whole thing is a dy problem. And of course, since this is a y problem, our bounds have to be in y values. So here, your y value is 0. And up at the top where they intersect, your y value is 4. So your bounds are 0 to 4. So here's the equation that you would go ahead and write down on your paper. Now, what do you put into your calculator? In your calculator, in your y1, you're going to put parentheses 2x and your parentheses, because this whole thing is what's being the cube root, or taken to the 1/3 power. So raised to the 1 divided by 3 power. Again, that power has to be in parentheses. Minus x divided by 2. You put this into your calculator with your bounds from 0 to 4, and you will still get an answer of 2. So now let's look at a quick problem where your top minus bottom of your rectangles, it changes. Notice in this problem here, in this first part, my top minus bottom is my blue function minus my pink. And in this one over here, it's the pink minus the blue. So the first thing you have to do is make sure you're graphing these functions so you see the difference. I also recommend using colors, if you can, to make it easier to see the difference in the two functions that you're graphing. First of all, we know we're going to set up a top minus bottom problem, and this is going to be a dx problem, because as you see here, these are tiny changes in our x values, which makes this a dx problem. The other thing you'll notice is I went ahead and I labeled all of my intersection points. Find those on your calculator. Notice they are not nice numbers here. Just round to whatever you need to and mark it down. Makes it easier when you're setting up your equation. So the first equation, we're going to do our top minus our bottom, our blue curve minus our pink line. So we're going to have our integral. Our top function is our blue curve. 3x cubed plus x squared minus 5x plus 4 minus parentheses x plus 4. You have to have those parentheses because that negative sign must distribute all the way through those parentheses. And then, of course, this is a dx problem. And what are our bounds? Well, this starts at negative 1.59, and it goes until when x is 0, because that's when the function switches from the blue one being on the top to the blue one being on the bottom. So this is the first part of that equation that you need. Then you need to add to it The second integral starts with now our line, x plus 4, minus our curve, 3x cubed, plus x squared, minus 5x, plus 4, dx. And of course, this one's going to go from 0, where the other one left off, to 1.26. So these are the functions that you're going to use. You put each one of them into your calculator separately, and then you're going to add the results. The first one, you should get 4.13. The second one, you should get 2.21. So you will have a total of 6.34. Hopefully this helps simplify area between two curves for you. Remember, first thing you need to do is graph the functions. Find their intersection points on your calculator. Set up the integral problem with top minus bottom if it's a dx, right minus left if it's a dy. Make sure you know who is the boss to decide if your bounds should be x or y values. Hopefully this helps. Make sure you share with a calculus friend.